Today we're going to talk about squares, square roots, and Pythagoras. But before we get started on new information, let's take a look back at some things that we already know. First of all, if I have a square, and I know that this is a square by giving my congruent marking tags, and let's say that each side of my square has a measurement of 4 centimeters, we know that there are two key ways or two easy ways to figure out its area. We can think of area as base times height, or in this case we can think of area as side times side, because each side is the same length. We can reduce this or compact this and say that area is equal to side squared. So in the case of the area of this particular square, if we have our area and we're looking at each side length or a side length and we're going to square it, our area is going to be 4 squared, which is going to give us an area of 16 centimeters squared. When we are looking for the area of a triangle, we do need to remember that we need our base and our height. So let's say that our base is 5 centimeters. And in order to find our height, remember that we have to drop or find and create a perpendicular height line. Let's say that that is 6 centimeters. And we know that finding the area of a triangle is base times height divided by 2. We can take our base, which is 5, multiplied by our height, which is 6. And after we multiply those together, divide them by 2. And here we can see that the area of this particular triangle is 15 centimeters squared. So there's just some quick things that we need to keep in mind before we continue on. When we are squaring numbers, we know that we are taking a number and we are multiplying it by itself. We can recall that we use exponents to write a number as a square number. So in the case here, we have our 5, which you'll remember is called our base. We have this small 2, which is the exponent. And if we were to think of this in expanded form, which is a term hopefully we remember, we can think of this as being written as 5 times 5, which is going to give us 25. So we can say that 5 squared, or 5 to the exponent 2, is equal to 25. So I want you to follow along with me as we take and look at how we can change or look at the number 49 as a square number in both symbols and words, and also as a diagram. So in symbols, this is pretty straightforward. We know that we have 49. We know that this can break down, or we can think of this as what number multiplies by itself to give me that 49. So I can think of 7 times 7, and I can rewrite that a little bit more eloquently and say that it's 7 squared. In words, pretty straightforward again. I could just say that 7 squared equals 49. Now the diagram part is something that you may not have too much practice with, so we'll make that one stand out a little bit. I know that I have a square, even though it may not look like one, and I can think to myself, if the area of my square, or the total size of my square, is 49, what then does each side length have to be in order to allow that 49 to be the area? So I have to think to myself again, what side length measurement do I need to multiply by itself in order to give me that area of 49? And again, that's going to be my 7 centimeters, or my 7. So this is another way that I can show this visually. In example 2, going to be asked to write each number in exponent form. So if I want to take 25 and write it in exponent form, I have 5 squared. What number do I need to multiply by itself in order to give me that 25? For 81, think, what number do I need to multiply by itself in order to give me that 81? That's right, 9 squared. What number do I need to multiply by itself to give me 64? That's right, 8 squared. What number do I need to multiply by itself to give me 169? That's right, 13 squared. Now the opposite to squaring a number is finding that number's square root. So if I think of 7 to the exponent 2, or 7 squared, I know that that equals 49, because I'm taking that 7, multiplying it by itself, so 7 times 7, which is going to give me that 49. If I think of finding the square root of 49, so this is the opposite way, I have to think to myself, what number multiplied by itself is going to give me that 49, so that's what we call a square root, and of course that is going to be 7. So together let's find the square root of 36. I can do this in numbers, I can do this in words, and I can do this in picture format like we did on the first page. So in numbers, I can think of this as being the square root of 36 is equal to, so I have to think to myself, what number is multiplied by itself to give me that even 36, and I know that's going to be 6. In words, I can write this as just simply the square root of 36 equals 6. And as a picture, again, similar to what we did on our first example on the first page, if I think of literally having a square, in this particular case, I'm thinking of the area being 36. I have to think to myself, what is each side length going to be? So if I was to multiply this side length by this side length, and those side lengths have to be exactly the same, what would they be? So I can write this as the square root of 36, or I can say that that side length is also 6. Now, what becomes a little bit more challenging is when I have numbers that are not easily divisible into whole numbers. So, if for example, you were asked to find the square root of 80, I have to think to myself, all right, what numbers are close to 80 that will give me a whole number if I find their square roots, and what numbers, and then how can I do a little bit of perhaps rounding to one decimal place to help me calculate this. So if I think of a number line, which I know we love so much, all right, the whole number that's going to be above this is 81, right? I know that 81 gives me a square root of 9, or the square root of 81 is 9. And the next closest whole number that I have is going to be 64, because that's going to give me a whole root number of 8. So I have to think to myself, where on that number line is this 80 going to be positioned? So this 80, obviously, because that's what I'm looking for basically the square root of 80, is going to be positioned way down there. So in terms of rounding this mentally to one decimal place, I might say that the square root of 80 is approximately 8.9. So when determining square roots in example 3, we can think what number divides equally into itself, or what number can I multiply evenly into itself to give me the square root of the number that I'm looking for. So in the case of the square root of 1, what number multiplies by itself in order to give me that 1? Correct, it's a 1. Square root of 25, therefore, perfect, is 5. Square root of 81, excellent, 9. Square root of 9, perfection, 3. Square root of 121, excellent, 11. And the square root of 225, super, is 15. Now, what's going to help us keep everything a little bit straighter is trying to understand and keep track of what to do when I'm given certain information and what to do when I'm looking for certain information. So we know that area of a square can be expressed as length times length, or we can write this as length squared. So when I know the length, right, what this is going to allow me to find is the length squared. So this is what I can find. So what that means is, if I have my square, and I know that the length is 2, so this is what I know that I can find length squared, or I can find the area by using that formula of length squared. So area equals length squared equals 2 squared. So the area of my square is 4. On the flip side of that, if I know the area, so this is what I know, what I can find is its square root. So this is what I'll be able to find. So if I have, again, a square, and I know that the area, or the size of the square, is, let's say, 16 centimeters squared, what that's going to allow me to look for is the length. So I can figure that the length is equal to the square root of the area. So each side length is equal to the square root of 16. Then I can think, what is the square root of 16? Well, that's going to give me a side length of 4 centimeters. So those are a couple quick little tricks to help keep track of what you have and what you might go looking for. The last topic we're going to cover today is how can I find the area and the side length of a square that is not sitting square on my page. So in this particular case, what I have is a square that has been rotated. And what I want to find is the amount of area inside of my rotated square and also its side length. Now, in the past, you might have figured out and counted all of the missing squares, but I want you to take a second and see if you can come up with a more eloquent or sophisticated way to figure out those side lengths. All right, so the trick to this is to actually cut out any additional information or sizing that you do not need. And what you'll see is I've actually created a regularly oriented square, a round that touches the corners of each of my turned square. And what that's going to give me is some small triangular pieces created outside of it. So what I can actually use is these triangular pieces and subtract these triangular pieces from this size to help me figure out this area. So here's how we can make this work. If I think of the area of the orange square, what I want to count, or what I want to look for, is to figure out that's area. I know that I can figure out the area by taking the length and squaring it. So in this particular case, when I count the size of my orange square, it has a side length of 1, 2, 3, 4, 5, 6, 7. So the orange square, if I was to take and look at all of it, including my rotated square, would have an area of 49 units. Now, what I want to think of is taking away or subtracting, right, the area of my triangular pieces. So you'll recall back to the beginning of our video, that area is base times height divided by 2. So if I look at this one over here, I have a base measurement of 3, a height measurement of 4, and I can divide that by 2, which is going to give me an area of, total area of 6 units. Now don't forget that I have 1, 2, 3, 4 of these little tiny triangle pieces, so I have to multiply that by 4. So what I have is a total area of my little triangle pieces of 24 units. Last thing I can do to figure out the area of my turned square is 49 in the big orange minus 24 in all my triangular pieces, which is going to give me an area of my rotated or turned square of 25 units. So when I scoot back up here, I can say that the area of this here is 25 units squared. And in order to figure out the side length, we talked about this before, I can think of length is equal to the square root of my area. So length is equal to the square root of 25. So the length of each of my sides of my rotated square is going to be 5 units.